Thank you very much for the introduction, and thanks for the invitation to speak and also the invitation to join this initiative. So yes, I will speak about black hole states and quantum spin chains, and what I will present will be based on this preprint that was written in collaboration with Konstantin Zarembo. So now I cannot. Okay, I have to do like this instead. So I'll start by giving some motivation, fairly detailed, first with some words as here, and afterwards with some images, and finally with some formulas. So what I'm aiming at is the computation of thermal correlators in ADS-CFT. It's of course interesting because it allows us to probe the dynamics of black holes, but we also have some technical motivation for approaching this problem, and that's because there exists a very efficient program for computing one-point functions in defect setups. And a thermal quantum field theory is another example of a setup where translational symmetry is broken and where you can have one-point functions. So we want to extend this program to the case of thermal field theory. And this program, it builds on the underlying integrability of ADS-CFT, and it will require us to identify what would be the spin chain equivalent of a black hole. And that is an interesting problem in itself. Okay, so first of all, the ADS-CFT correspondence itself, it provides us with a common framework for quantum field theory and string theory. And part of this framework is that the quantum field theory and the string theory share the same spectrum. And furthermore, this common spectrum of the quantum field theory and the string theory can be identified with the spectrum of a much simpler system, namely a quantum many-body system in the form of an integrable spin chain. Okay, so this framework comes with a lot of symmetries, and of course one can wonder to what extent ADS-CFT and integrability still holds if you try to break some of the symmetries. And one way of breaking symmetries is by introducing defects. And an simple example of a defect could be a domain wall, which separates two regions of spacetime where the theory is in different vectora. So we know what that corresponds to on the string theory side, namely it corresponds to introducing a probe brain in the string usual ADS-CFT background, a probe brain which does not disturb the background and which intersects our four-dimensional Minkowski space in a three-dimensional subspace, which is exactly the domain wall. It's also been understood what in the introduction of a defect or probe brain corresponds to in the string theory language, namely the domain wall, respectively the probe brain, has to be represented by what is known as a matrix product state. So it's a spin chain state where each spin configuration or each spin value has a certain matrix associated to it, represented by these A's here. Then you take the product of matrices and sum and the trace, and that's the coefficient of the corresponding spin chain state. There will be some formulas explaining this later. So what we want to do is to now, instead of introducing a defect, introducing a temperature in the quantum field theory. And we know very well what that corresponds to in the string theory, namely it corresponds to introducing a black hole. And the question I want to ask is, what does this correspond to in the quantum spin chain? What kind of state would represent the black hole in the spin chain? That is what I hope to answer during this seminar. Okay, so let's be a little bit, go to the next level of detail, so to say. So the ADS-CFT correspondence, it states that there is a one-to-one correspondence between conformal operators in the quantum field theory and string states in the string theory. And the way in which integrable spin chains enter the picture is that the good conformal operators in the quantum field theory in the planar limit of the theory gets identified with the eigenstates of an integrable spin chain. more precisely an integrable superspin chain. And of course, the same holds for the dual string states. So the main example of this is in the original ADS-CFT correspondence, which involves Enrico's four super-Yang-Mills theory in 4 dimensions on the quantum field theory side, and that is the example I will have in mind. Okay, so the eigenstates of the spin chain I will denote by U, and they are in one-to-one correspondence with the good conformal operators in the quantum field theory. So now I introduce a defect in my quantum field theory in the form of a domain wall. It can also be a more general, just flat codimension defect. And that, as I already said, corresponds to introducing a probe deep brain on the string theory side. Now it turns out that the domain wall and probe brain in the spin chain picture has to be represented by a matrix product state, in the sense that if I take the overlap with that matrix product state, which is a spin chain state, with the spin chain eigenstate, which represents the operator O, then I get exactly the one-point function of that operator. Okay, and now my idea is that I want to generalize this to the Thurman quantum field theory. So I want to see what kind of state in the spin chain represents the black hole, in the sense that if I take the overlap of that state with the eigenstate representing the good conformal operator, then I get exactly the thermal one-point function of that operator. I hope it's kind of clear. Okay, so now just a little bit of background about the spin chain language. So a state in a spin chain, I will just denote by listing the values of the spins at various sides of the chain, like this. And then I will assume that it always has periodic boundary conditions. The eigenstates of the chain I will denote by U, and that's because in the integrable case, such as eigenstate is parameterized in terms of some rapidities, which are typically called U's, and they solve a set of algebraic beta equations in the integrable case. So a matrix product state is just a particular state of the spin chain, where you sum all possible spin configuration, and for each value of your spin, you associate a certain matrix, and then a particular spin configuration comes in the sum with a coefficient, which is simply the trace over the corresponding matrices, like this. For instance, if you have just a Heisenberg spin chain with a spin up and spin down, then you can associate a matrix T1 to spin up and a matrix T2 to spin down, and then the matrix product state would simply be this one-side product state, taken with itself L times. Okay. And just a few words about ADS-CFT integrability. We only need the content of the very first paper, which led to all the development about ADS-CFT integrability, namely the paper by Minahan and Sorembo. So it deals with the scalar fields of N=4 super-Yang-Mills theory, of which there are 6, and discusses the good conformal operators that you can build from these scalars. And what was shown was that at the one loop order and the planar level, then the good conformal operators, there are linear combinations of single trace operators. And this linear combination is supposed to be such that the operator is in one-to-one correspondence with an eigenstate of the integrable SO6 spin chain. And it's an SO6 spin chain because there are 6 different fields and 6 different spin orientations in the spin chain. And the mapping is such that some order of fields by I1 up to phi IL is mapped onto a spin chain state in the obvious way. And the eigenvalue of corresponding to the particular eigenstate in question is then the conformal dimension of the corresponding good conformal operator. Okay. Now let's say that we want to introduce a domain wall in this setup. And it could be a wall which separates 2 regions of space-time where the field isn't where the theory is in different vector. So maybe on one side of the defect, we have a trivial vacuum, whereas on the other side we have a non-trivial one, where the scalar fields get some classical expectation values. And typically in this type of setup, one has introduced a space-time dependence on the VEVs, because this will conserve conformal invariance on the defect, and the whole setup becomes a defect CFT. Now, in such a setup, you can of course have one-point functions already at tree level, and you find these one-point functions of your good conformal operators by taking the good conformal operators and plugging in the classical values of the fields, like I wrote down here. And this process I can formulate in a convenient way using a matrix product state. Namely, I introduce the matrix product state written down here, where again I sum over all spin configurations of the SO6 spin chain, and for each spin I associate a matrix, and then the coefficient in this expansion of a given spin configuration is the trace over the product of the corresponding matrices. And then if I take the overlap of this matrix product state with the spin chain state representing my operator, then what this matrix product state does is to pick out in the eigenstate this term which has the same order of the spins, and then it replaces it with this trace over matrices. And that is exactly the product process up here of computing the one-point function. So I can simply write my defect one-point function as this matrix product state overlap, where I have left out some normalization factors, but I have left around this 1 over x perp to the power delta, because it's important that in the defect setup we have a certain scale, which here is the distance to the defect, and which in the thermal case will be the temperature. Okay. Now it turns out that sometimes this overlap, which gives the one-point function, can be found in closed form, and one then says that the matrix product state is integrable. And it's by now very well understood what it means for a matrix product state to be integrable. And one has an easy test that one can perform to find out whether it's integrable or not. And if it is, one has a specific procedure for how to compute the overlap. So to test for integrability, one makes use of the fact that one has an underlying integrable spin chain, which means that that spin chain has L conserved charges if L is the length of the chain, and these commute with each other and with the Hamiltonian. And it's understood that a matrix product state is integrable if there's an infinite series of these charges which annihilate the state. Infinite in the limit where the length of the chain goes to infinity, of course. And specifically for this domain wall setup, the matrix product state is integrable if it's annihilated by all the odd charges. But in practice, it seems to be enough to check that it's annihilated by the first odd charge. There are, as far as I know, no counterexamples. One can also formulate it more precisely, and this is a formulation which resulted from several years of investigations and more refined methods to compute the overlap. And this optimized form of the procedure is something which was formulated by Thomas Gomborg. And what you have to do to check if a matrix product state is integrable and find the overlap is, in precise terms, to find an object K which fulfills this relation here, which is known as the KT relation. So it involves the matrix product state now with the trace cut open, so that there are two boundary indices. It involves the transfer matrix of the underlying integrable spin chain, which acts directly on the physical space. And then it involves this object K, which has both a physical index and some boundary indices. If one can find such an object, then the matrix product state is integrable, and one can extract from K the overlap in closed form. And moreover, it turns out that this overlap always has the same universal form, which I will not go into discussing because I've discussed it many occasions before, but it's a very beautiful closed formula which just depends on all these rapidities that characterize my good conformal operator. Okay. So let me now move on to the main topic, namely thermal correlation functions. And I will concentrate on thermal one-point functions because that is what my formalism is good for. So I consider my good conformal operators built from scalars in n equals 4 super Yang-Mills, of which there are 6. And now I want to compute the one-point functions. So I can simply follow the field theory recipe and make my big contractions. And the scalar fields, they are adjoint fields, so they are contracted using usual matrix model contraction rules, which involve these delta functions here. So the space-time dependent part of the propagator I get, of course, by going to Euclidean time and compactifying on a cylinder of radius beta, which is 1/4 the temperature. And then I get the space-time dependent part of the propagator as this sum here over different modes. Okay. And again, to be able to use the spin chain picture, I restrict myself to the planar case. And I'm then allowed to make planar contractions between the various scalar fields. And down here, I have written down the case of where the length of the operator is 8 and where I make a number of planar contractions. So they are, of course, contractions where these double lines here do not cross each other. But of course, all the fields are taken at the same point, since I'm talking about a one-point function, so I should rather draw my diagram in this way here, where all operators radiate from the same point. So what it produces me are some diagrams which have a lot of loops which start and end at the same point. So each of these loops give the same contribution. So the total value of my diagram is simply the value of this loop to some power which is equal to the number of contractions that I made. Of course, there's a divergence if I'm at 0 temperature, but I'm interested in the thermal effect, so I'll just, for the moment, subtract the 0 temperature part. So the 0 temperature part corresponds to the mode number n equals 0. And if I subtract that, then I get this result here for one of those loops that I showed before. There's no space-time dependence because, of course, it's the loop that starts and ends at the same point. And that sum over mode numbers is a finite sum, and it evaluates to 1/12 beta squared. Okay. So now I've accounted for the space-time dependence of the one-point function, and I want now to account for the combinatorics in the contractions. So I want to construct a boundary state, a black hole state, which counts the number of contractions that I can make for the type of diagram that I just showed. So it obviously has to be a state in the SO6 spin chain. So it's given by some spins and some coefficients. And as these coefficients, I can simply take the large n limit of the following matrix integral, where these matrices are Hermitian matrices, and they are just given in terms of a Gaussian interaction, because this produces exactly those planar contractions that I showed before in the large n limit. And here I take two identical fields, because also in n equals 4 super Yang-Mills, I can only contract identical fields. You can also notice that since I contract only identical fields, my black hole boundary state, it picks out singlets of my inside my operator. And we can say that this is actually a random matrix product state and not a finite matrix product state. And using this random matrix product state, I can formulate my thermal one-point function as an overlap between that state and the spin chain eigenstate, which represents the operator. And then there are some prefactors which are inserted in order to take into account the good quantum field theoretical normalization of the two-point function of the operator. But you can notice here that, as I announced before, the temperature now appears in front of the one-point functions as our scale. I don't know if there are any questions, because this is somehow the key point.
Maybe one, but I'm not sure how to formulate it exactly. But the fact that your computations before are classical, how should I understand that?
I'm just working at the lowest loop level. I mean, this is a classical computation, but I say that my quantum field theory contribution is just a product of loop diagrams, which all take the same value because they start and end all at the same point.
Yes.
So each of them
So
is 1 over 12 beta squared, each contraction, and that is what gives rise to this t to the power L in front of the 1-point function.
is the shape of this last formula, with especially the last factor with the superposition of states, would it survive beyond this classical calculation, or is it really just at this level?
It is for the moment only at this level, but the hope is, of course, that one can do the same as for the defect setup, or one could actually bootstrap it to all orders in the coupling constant.
Mm-hmm.
For the moment, it's just the leading order result.
Okay. Thank you.
Okay. So let's look a bit more carefully at this black hole state then. As I said, it's built from SO6 singlets because I'm only allowed to contract identical fields, and I sum over all fields, which produces me an SO6 singlet. And I can also construct it recursively by starting from one SO6 singlet given by these two eyes here, and then inserting smaller black holes in between in such a way that the contraction is still planar, of course. And that happens automatically in this with this recursion here. Then one can, of course, start by wondering whether this black hole state is integrable in the same sense that the defect matrix product states were integrable. And to do that, one has to rely on the underlying integrable SO6 spin chain. So you need to identify its third charge, but that's well known. If you write its Hamiltonian in this way here with a nearest neighbor Hamiltonian density, small h, then the third charge is simply given by this sum here over densities. That's completely concrete, and you can apply it to the black hole state, which is also completely concrete, and you will find that it doesn't kill the state. So the black hole state is not integrable in the sense that we know. So, and that is exactly as expected. We do not expect that black hole to be an integrable object, so to say. So therefore, we have to study it by other means. So let's try that. But the SO6 black hole is a complicated object. Let's start with something simpler. So let's start with an SU2 black hole state. And that is a black hole state in this U2 spin chain. So how would we mimic the SO6 black hole state? Well, we would build this SO2 black hole state from singlets. But of course, a singlet in SU2 is different from an SO6. So it takes this antisymmetric form, as you know. But we can still construct the black hole state recursively, starting from a single singlet here, formed in terms of alpha, epsilon alpha beta, and alpha and beta, and then, well, which corresponds to this arch here, and then under the arch or besides the arch, we can put smaller singlet contributions so that we still respect the planarity of the contractions. Again, we can construct our black hole state as a random matrix product state. But of course, in this case, it's a spin chain state in an SU2 spin chain, so all the spins can only be up or down. And the random matrix model that we need to count the contractions, it actually has to be a random matrix model involving Grassmann valued matrices. And that's because this antisymmetric contraction that we need to make to form the singlet, it doesn't go well with the cyclicity of the trace. And therefore we have to use Grassmann variables instead. Otherwise, the trace is killed by the antisymmetric contraction. But in this way here, we get exactly the combinatorics that we need. But let me say that this SU2 black hole state, it does not really have an interpretation as something generating thermal 1-point functions in n equals 4 supernomials. That's only really true for the SO6 black hole state. But nevertheless, let's start by studying the SU2 black hole. So let's look at some of its simplest properties first. So first of all, one can determine what is its momentum. So the momentum in the spin chain language is just the first conserved charge, or it's a one-side translation operator. And it's quite easy to show that if you translate the black hole state by one side, you get minus the black hole state, which means that the state has momentum pi. Furthermore, we can apply the first conserved charge of the SU2 spin chain to the black hole state and see if it's killed or not. And it's not. So again, black hole state is not integrable as we expected. So therefore, we will study it by some other means. We will look at various complexity measures to try and characterize it. So we will look at the entanglement entropy of the black hole state, of its thermalization properties, and its Krylov complexity. Okay, let's start with the entanglement entropy. So that is something you can easily define if you have a Hilbert space which splits into a direct product space. Then if you have a state or density matrix on the full space, you can define a reduced density matrix by integrating out or tracing over part of the space here, B. And then the entanglement entropy of the region A relative to B is defined as this quantity derived from the reduced density matrix. And that is actually something which fits very nicely for a spin chain state. Namely, you naturally have a split into two sub-Hilbert spaces, and you have a natural orthogonal or orthonormal basis in each subspace, namely some smaller spin chain Hilbert space. And if you write your initial state as a big matrix in this direct product Hilbert space, then the reduced density matrix is simply this matrix times its Hermitian conjugate. And this matrix can, of course, will of course be in general rectangular, because the two Hilbert spaces need not be of the same size. But it's something you can easily compute, this reduced density matrix, and then you can, of course, determine its eigenvalues and extract the entanglement entropy. And this we want to do for the black hole state. And we want to contrast it to some of the integrable states that appeared in the defect setup. And we want to, well, in this SU2 spin chain, all two-side product states are actually integrable. They're also known as valence bond states. And we will take one which resembles the black hole state most, so to say. It's one where you just take a product of, as your wave function, take a product of epsilon symbols that corresponds to, in the contraction language, to just making nearest neighbor contractions all along the spin chain. And then you take that one in combination with its once translated version, because you also want something which has momentum pi. And that's a state that we want to all the time contrast with the black hole state to illustrate the complexity of the black hole state. Okay, so we can compute explicitly the entanglement entropy using this recipe. And this is what the result looks like if we consider a spin chain of length L equal to 20. And then, well, we cut it in two pieces, where one of the pieces has length, this curly L. And one curve is for the black hole state and the other one for the integrable state. And you see clearly there's a huge difference here. The entanglement entropy saturates at 2 log 2 for the integrable state, which is kind of understandable because we have two pairs of spins which are entangled across each of the boundaries of the piece that we cut out of the chain. And the same will be the case for any other integrable two-side state in the chain. But the matrix product state, it shows a more interesting behavior. Not the black hole state shows a much more interesting behavior. Its entanglement entropy appears to be growing with L and not saturating, and therefore we try to look more into this behavior. Here's again the a figure of the entanglement entropy for the black hole state for length 20 as a function of the cut out length. And here, this curve, it fits extremely well to an expression, logarithmic expression, which takes this form here. And this expression is something which was derived by Cartier and Calabrese by CFT techniques for the ground state of a critical system. So it depends on the length of the system, but also it has this functional behavior of this curly L here. And in that CFT, from that CFT derivation, this constant C here has an interpretation of the central charge of the underlying model, whereas this C1 prime here is a non-universal constant. And we can extract this constant C from our plot, and it appears to be 5.2. We're not sure exactly what this means, if it makes sense to associate a central charge with a black hole state like this, but definitely there's something interesting going on, and it would be nice to derive this formula starting directly from our black hole state. Okay, let's move on to another investigation of the black hole state, namely its thermalization properties. And we will do that on the background of the eigenstate thermalization hypothesis. It says that if you have a sufficiently generic state and some local operator, then the time average of that local operator will be determined by the density matrix of the thermal ensemble. So it will be given by this expression here. And that result builds on the fact that this of the ETH, which states that this average can be calculated entirely in the diagonal ensemble, taking into account only the diagonal elements of the operator A. This kind of relation here is not really expected to hold for integrable systems. They're not supposed to thermalize because there are other conserved quantities than the energy, and therefore the thermal distribution would look differently, or there would be no thermal distribution. But nevertheless, we will try to claim, or we sort of find that the thermalization still takes place, but at infinite temperature, and we illustrate that by computing the prediction of the ETH and comparing with a numerical experiment based on an operator which is known as the emptiness formation quantity. Okay, so the operator that we will consider is this operator A, which is the product over n spin change sites, and it gives a 1 if the n sites all have spin up, and otherwise it gives 0. And it's called the emptiness formation probability because it was originally defined with a minus, and at some point spins down were known as empty sites. And that's where emptiness comes from. And then, of course, if you average it, it becomes a probability. Okay. And we claim that the thermalization happens at infinite temperature. And that means that the density matrix, the thermal density matrix, is simply a uniform distribution. So it's simply nothing but a projection onto the singlet of the SO2 spin chain. That's our claim. And we can easily write down concretely what that projection is. This ClO2 is a Catalan number. It's the total number of singlets. The Catalan numbers are actually exactly the solution of that recursion relation I showed earlier. And the projection operator we can also write down explicitly in group theory language. So here G is a generic SU2 matrix and DG is a Haar measure. And if you parameterize the SU2 matrix in the standard way, this is just an integral over the 3 sphere. So that's something you can actually compute, and you can also compute the trace up here that is needed for the ETH. Okay, here I have written down what the computation entails. We need the infinite temperature density matrix and this emptiness formation probability objects, and the joint action of the two simply gives rise to this expression here, where the integral, it comes from this integral over the group that I had in the projection operator on the previous page. And this split into n and L minus n, of course, comes from the fact that we have this emptiness formation operator, which involves n spins. And this is a simple integral that you can compute, and it gives some combination of factorials. And you can take the L infinity limit of that expression, keeping n over L fixed, and then you find that this quantity is decaying exponentially with length with some function here, which you can also exactly extract in precise form. So that's a prediction. And we wish that to compare that to the direct computation of this quantity here, the time average expectation value of our operator. So this is something we can simply do by taking our black hole state and computing these overlaps with the eigenstates of the spin chain. And here's what the result looks like. So in this curve here, the analytical prediction is a solid curve, and all the scattered dots are the results of the numerical computation of the matrix elements, and that is for various lengths. So apart from the fact that the dots are a bit scattered due to the finite length, at least the qualitative feature of the curve is reproduced. And since we have an underlying integrable system, we attribute this summarization not so much to the underlying system, but to the black hole state itself. And this we somehow support by also doing the same computation for a non-integrable version of the spin chain. So you see, here we've done the same plot, now for length 16, but both for the integrable and the non-integrable version of the spin chain. And you see there's not much of a difference between the integrable and the non-integrable case. So we sort of interpret the fact that this curve is more or less followed by our black hole state as a property of the state rather than of the underlying spin chain. Yes. Okay.
Sorry, just one quick. Here you don't expect the two dots, the lambda equals 0 and lambda equals 1 to agree, right?
No, because one case is an integrable, nearest neighbor is spin chain. The other case we take next to nearest neighbor chain and tune the coupling so that we are sure to be in a chaotic regime. I'm just showing this to show that there's not so much difference between the integral and the chaotic case. So the features of this curve is more due to the state itself than the underlying spin chain.
Good.
It's a property of the
So
state.
just to be sure, so you're using the same, let's call it black hole state, right? For the two?
Yes. Yes.
Okay. I see. Okay, thank you.
That's right. Okay, so the last thing we looked at was the Krylov complexity. And again, we tried to contrast it between the black hole state and the integrable valence bond state. And the Krylov complexity of a state is a measure for, well, for the complexity of the state, but also for how far the state moves away from its initial value as time passes. So let's look at it. So if you have a normalized state to define its Krylov complexity, you first define the Krylov space, which consists of the span of these vectors here, which are generated by acting with the Hamiltonian a number of times. Then there's an algorithm which is known as a Langton's algorithm, which generates for you an orthonormal basis of states in this Krylov space. And this basis has property that the Hamiltonian is tri-diagonal in that basis, and this sort of has the form of a hopping interaction. Then in that basis, you study the time development of the initial state, and you define the Krylov complexity as the average of the distance from the initial state measured in that basis, where the initial state is the first step, so to say. Then you can define a time average version of it by integrating over time like this way, or averaging over time like this, in this way, which is something you typically do to avoid too many oscillations that you sometimes have. Okay, so here we have plotted the Krylov complexity for respectively the black hole state and the integrable state. And what we see is that it grows faster and it saturates at a large jump value for the black hole state compared to the integrable state. And that is more or less all we can say from that plot, at least as it has some nice qualitative features, but we don't dare to say much more because the available Hilbert space for the black hole state actually only consists of 69 states. There are only 69 singlet states with momentum pi for a spin chain of length 16, which is this chain that we consider here. But it would be interesting to do this for much bigger systems. And
sorry, I have a quick question. Maybe I'm misreading the scale of the plot, but I thought there were statements that the complexity of a black hole should saturate exponentially in the dimension of the Hilbert space. Sorry,
yes, the first part of this curve here should be exponential. That is what you mean?
No, sorry. I'm just comparing the scale of entropy saturation with the scale of complexity saturation. So the entropy grows like yeah, maybe I'm misremembering the scale. Yeah, I thought somehow the complexity should be exponential in the entropy. Is that what you're finding for what these black holes state saturate as?
But this is the Krylov complexity. I don't really know. You're talking about entropy or what?
No, I'm comparing complexity and entropy.
Yeah. Okay.
Is it difference? I see. Okay. Okay. I didn't appreciate that Krylov complexity was different. All right. Sorry. Thanks.
Okay. I think more if there's something to say about the comparison, but okay. We don't try to make any strong conclusion from this plot. Rather, we just want to see the qualitative difference between the states. Okay, so that actually leads me to my conclusion. So what we've done is that we have identified a spin chain boundary state that we denote as a black hole state, which encodes the thermal one-point functions in the ADS-CFT correspondence, in the sense that if we take the overlap between that state and beta eigenstate represent a good conformal operator, then we get the one-point function of that operator. And ADS-CFT is, of course, a little bit of an overstatement because this is something that works only at the leading order for the moment. We have studied its complexity properties and found some curious results. For instance, we find the logarithmic scaling of the entanglement entropy very curious, and also the fact that we see thermalization at infinite temperature. And what one could dream of doing in the future is, of course, to extend all this analysis to the real black hole state of the ADS-CFT correspondence, namely the black hole state of the SO6 spin chain. And that should be simple. It's just a matter of more time and computational power. Then, of course, there are many other quantum many-body systems where one could define similar black hole states by building it up from singlets in a planar manner. And finally, one could also try to study quantum quenches where one uses black holes as quench initial states. These matrix product states, which represented defects, they have been used a lot to study quenches with the corresponding states as initial states for the quench. Thank you very much for your attention. That's all I wanted to tell you.